Okay.
Start recording and then present the speaker.
That's it. Okay.
And make sure I can share my screen.
Oh, yes. Do you want to try it out?
And there it is.
Okay, great. Could you take it off just for a second so I can finish this part?
Mm-hmm.
Okay. So Casey Kennington was born in Ontario, but not in our Ontario, in Ontario, Oregon. And he is, in fact, a computational linguist and a roboticist. His interest is in how we understand language, how we learn language, how we acquire it, and the interaction, which, I mean, language is a form of communication, a very special form of communication, the interaction between linguistic interaction, verbal interaction, if you like, between entities, and I really say entities that use language. He's also interested, and this interests me too, I don't know how much you're going to talk about it, Casey, but he's also interested in nonverbal behavior, because language is a form of communication, a very special form. But there's other forms of communication that we share with lots of other species. In fact, I'm curious to hear whether the Bielefeld camp of linguistics thinks that non-human species are capable of anything like language. But at any rate, these are all of his interests, and they all come together in the cognitive science era in what we could call cognitive robotics. How do you get robots to do the stuff that we do? And for people in cognitive science, how robots do it is a clue as to how it is that perhaps the human brain does it. I don't know to what extent that's a motivator for our speaker, but it's a motivation for the entire program, if you like, of cognitive science. And with that, I would like to welcome and thank Casey for coming and to give him the floor.
Thank you, I appreciate that. And to answer that, it is my primary motivation to understand human brains, I guess, even though I'm not a neuroscientist. I don't do stuff directly in cognitive science. I'm more on the computational side. But I think we can answer a lot about who we are by conveying and putting stuff into machines, and I'll talk about that. So my talk is towards understanding, dialogue, robots, and meaning, and how those things play into understanding, I suppose. So these are some questions that keep me up at night. What is language? How can children learn it? How do words come to mean what they do? How do humans learn meaning? How do humans represent meaning? Why is speech so different from written text? Why is language so ambiguous? What does it mean to understand? And how can we get a machine to understand? And I'm not the only one thinking about these questions, and these aren't the only questions keeping me up at night, but they're the ones related to my research that make me think. And they're fun questions to think about, and I really enjoy the fact that I can wake up in the morning and think about these questions, and someone is willing to pay me for it. Because the limit of my speech, or the limit of my language, is the limit of my world. And that's some well-known stuff by Ludwig Wittgenstein. And it's not, of course, completely true that all of our words, we only think in language. There's also a lot of other things we think in. But there's something to it. There's something to language. Once we crack language, I think we can crack a lot of other things, and vice versa. Let's talk about learning words. What was your first word? Children commonly learn words that denote physical objects, like people, body parts, common objects. So like, turn on this pointer here. Here's a child, here's a object. The child doesn't know that it's called anything. The child just knows that the child can play with it. Maybe the child has seen it, touched it, experienced it tactily, maybe even licked it, who knows? And someone says, ball, it's a ball. And this child keeps hearing this word ball in conjunction with this particular entity. And it turns out that that's pretty common where kids learn a lot of their language. And a lot of those words are concrete. Words that denote or refer to physical things are concrete words, like ball, toes, whatever. Concrete words are first learned through person-to-person spoken interactions. And there's quite a bit of evidence on this. You can, of course, learn concrete words abstractly and then see them in their real form later. Like someone can say, well, oh, you've never seen a zebra. A zebra is a horse with stripes. And then later you see a zebra and you know it when you see it, even though you haven't actually physically experienced it. But concrete words are largely learned by children at first. And it's through spoken person-to-person interaction. And children learn concrete denotative words first, and then non-concrete abstract words that don't have physical denotations come a little bit later, but of course, both are learned throughout life. And I don't know a lot about this. This is stuff that I'm getting into kind of recently, and I'd love some more discussion on this, but I'll bring up this theme a little bit throughout my talk. So some requirements for learning a language, and this comes from Herbert Clark. It's situated in that multiple people are in a co-located situation. There's shared attention, there's didactic pointing gestures, there's saliency involved, so things that are kind of attention grabbing. Speech is the primary medium. You don't sit a child in a room and throw books at them and say, go learn language, even picture books, or even put them in a room with a TV where there's objects being talked about on the television, and they don't learn language that way. And there's actually been some research on that. Participants agree on denotative words to concrete concepts. Generally, a child takes an older person's words as what is agreed upon. So there's some trust, some Gricean trust there. I mean, I have a 2-year-old son, and I could go to my 2-year-old son and say, oh, this is this, or this is that. I can totally make up a language with my son, but it wouldn't be doing him any favors because it's more useful to him to learn a language that other people use in a larger community. And agreement happens through updates of use, and this update of use happens throughout life. And this is kind of word meanings shift over time as well, and that shift happens because of update of use. So words can denote any physical feature too. It can be visual features, tactile features, olfactory, proprioceptive, interoceptive, and you can just list all kinds of things here. So how can we convey linguistic semantic meaning to machines? That's my big question. And that's the question that a lot of people are thinking about right now. So let's talk about semantics. Semantics is the meaningfulness of language lies in the fact that it is about the world. And a lot of people have said similar things to this. I'm quoting Kathleen Dahlgren. And I want to bring up a little bit about how my field of natural language processing approaches semantics. And semantics is traditionally in linguistics the meaning side of things. So how do we convey meaning to machines from a computational linguistics / natural language processing perspective? Well, I took a class during my master's in semantic theory, and we were taught all about formal semantics, things like logical forms, first order logic, lambda calculus, discourse representation theory. And these were great for things like inference and quantification, and captured some aspects of language, but not a lot of others. In fact, the ones that I thought were the most important weren't captured. For example, we were taught you could take an utterance and translate it into a logical form, maybe using machine learning or rule-based systems or whatever. And the form would look like this. If I'm in the room with a child and I say the word red, and there's an object that's red and the child's looking at it, the child presumably, or at least a machine that takes the place of a child would presumably create some logical form or translate to some logical form, like there exists an X such that X is red, and be able to determine the red objects in the room. So I raised my hand and said, how does red know to return true or false? And my instructor said that doesn't really matter. It's all about the logical forms and the relations between them and the connectives, like the ors and the ands and the implications. And that bothered me to no end. Said, well, that kind of matters. Red needs to know if it's returning true or false, doesn't it? Well, no, not really. Yes, it does. Anyway, so I didn't do very well in that course. Another approach, which has gained amazing traction since 2013, is distributional semantics. Distributional semantics basically posits it's the you know the meaning of a word by the company it keeps. That's the Firthian notion. Words are represented, and the way we convey that to machines is words are represented as vectors based on lexical context. So instead of this very symbolic formal system, now we have this high dimensional vector. And this is amenable to classifiers. It's easily trained on text. You can grab all of Wikipedia, pick your language, and you can come up with these vectors. And you've probably heard of some of them, like Word2Vec, Glove, FastText, Elmo, BERT. And these things are amazing, and they're trained, and they do amazing things, and they have really advanced the field of natural language processing. They largely used neural networks. But there's some issues with this that I take. One is that there's no notion of the physical world. Like I can take the vector on any of these, take the vector for red, and I can't like hand it an apple and say, is this apple red? It doesn't know. So there's no competency of actual redness. It only knows that red things cluster with other red things, or with other, the word red clusters with other colors. And I think I'm saying that it assumes words are abstract. It assumes that the meaning of all words are all abstract because it takes them from text, and text are just symbols. And it does a really good job with that, but these are basically n-dimensional vectors floating around in n-dimensional space. And they're really nice, obviously, because we can take something like the vector for king, subtract out the vector for man, add the vector for woman, and you end up with the vector for something close to the vector for queen. So these relations have some value to them. There's some meaning there, but the notion of kingness or queenness or what that looks like when you see it, that's not quite captured. And there's been some recent criticisms of distributional semantics. I don't spend much time with that, though I'll show you something towards the end of my talk about some of the things we're doing. Then there's grounded semantics. You may have heard of grounded. The word ground comes from this paper that was written in 1990, you may have heard of. And the idea is that it links language to the physical world. A lot of the stuff that I've dealt with kind of makes the opposite assumption about meaning from distributional semantics, in that it assumes that words are concrete. So you give it a lot of training data, and words are linked to the visual world for the most part. And it's hard to train and learn because coming by data is much harder. And I'll talk a lot more about it.
Casey, could you just explain in a few words what you mean by concrete and abstract, so we have something to fill in?
So let me go back here. Words that denote physical things are concrete words. And abstract words are don't have physical denotations. So examples, concreteness would be like ball, toes, red, green, those kinds of things that you see, feel, touch. And abstract words don't have physical denotations. They're defined by other words like democracy and utopia. You can't take your 3-year-old or even like a 6-year-old even and say, little Billy, this is utopia right over here. So because there isn't a physical manifestation of utopia anywhere. Is that sufficient, do you think?
Yeah, it wasn't for me. I think that it's important to make it concrete, what you mean by concrete.
Yeah, thanks.
I was going to ask the same question.
Okay, good. I'm glad you asked that question then. And the next thing I ask then is, if we put all these three things together somehow in a unified framework, would that make a holistic semantics, or is there still a lot missing? So I want to explore that a little bit, and I do explore that a little bit in my research. In order to get into my research a little bit, I need to define understanding. Understanding is a psychological process related to an abstract or physical entity, whereby one is able to think about and use concepts to deal adequately with that entity. Understanding is a relation between the knower and an object of understanding. I actually copied this unceremoniously off of Wikipedia because I couldn't find a definition of understanding that I liked any better than this. So it might be a little bit vague. It's a psychological process, and we know it when we experience it, understanding. And that's the challenge. It's almost like it's a concrete concept that we experience. But there's also cases where we think we understand and we don't. And the hard part is that if you think a machine is understanding, it doesn't know that it's understanding. And that's the thing that we need to get to, is that the machine understands and it knows that it understands. So if understanding is my goal, my kind of long-term theory hypothesis is that we need to come to some sort of holistic unified semantics. And that's necessary for my field of computational linguistics, natural language processing, to get to an understanding. And I'm not saying that my field is the only field that's going to get there. There's going to be a lot of work from many different fields. But let me set up how this happens, I think. I took that semantic theory course that I told you about and didn't do very well in it. So I decided, well, if this is what people are saying semantics is, I don't think they're asking the right questions. So I wanted to go do a PhD to figure out what the right questions are. And that took me to a place that exists in Germany called Bielefeld. And there was a researcher there who worked in spoken dialogue systems. Let me tell you a little bit about spoken dialogue systems and why spoken dialogue systems is important for understanding. Because the setting of first language acquisition for child to caregiver is speech. And the way traditional spoken dialogue systems work is they have a microphone of some kind, some way of detecting the audio of the world, and then that gets transcribed through an automatic speech recognizer. The transcription, word 1, 2, and 3, and so on, comes out of the speech recognizer, and then there's a language understanding component. And this is where the semantic module goes. This is where kind of the language understanding happens. Right now, it's kind of in scare quotes. We call it understanding, but is it really? And that outputs some sort of a meaning representation. It could be a logical form. It could be a set of vectors. It could be some sort of grounded representation. It could be a slot value matrix. And then there's a dialogue manager that makes some kind of a decision on what to do next. Then there's something that formulates what is to be uttered, and then something called that's natural language generation. Text-to-speech is speech synthesis that actually utters it, so it comes through the speakers. This is your traditional spoken dialogue system. And this is kind of how Siri or Alexa works. You invoke them, they listen to you, they transcribe, and then they do something and make an action. The problem is humans don't do that quite that way. To kind of separate these two. There's spoken dialogue and then there's incremental spoken dialogue, because when humans are listening to each other speak, they don't wait for silence like Alexa and Siri does. You're not sitting there as I'm speaking, waiting for me to stop talking, and then you take all of my audio in your memory and then process it. That's not what happens. You are processing what I'm saying as I'm saying it as much as possible, as early as possible. So incremental dialogue systems are, in order to design those are much harder. The speech recognizer has to give out sub-utterance units like word level or even phoneme level. Language understanding component has to take those in word at a time and update its information state and output information at different time frames instead of an entire utterance. The challenge with incremental spoken dialogue systems is if you're not waiting for the entire utterance, you're going to make mistakes, and they do. The speech recognizers make mistakes. So in order to deal with these mistakes that could be made in light of new information, there need to be mechanisms for updating, which makes it harder to model. I'm not going to go into that. There's nice frameworks for it. But the point is that if we can do this perfectly, we have word by word recognition, speech recognition, word by word level, language understanding, and word level actions. And people like these. People who use incremental dialogue systems like them better than non-incremental ones. So that's a requirement, I would say, for getting at this holistic semantics and getting the setting right. But another part of it is that speech isn't the only modality. We also need to open the eyes of the system and have it interact with its environment, not just its eyes, other sensory inputs. But the example I give here is if you have a camera of some kind that goes into some kind of object detection, and then the language understanding component can maybe put the two things together, language and the visual world. That's at least getting closer to holistic semantics, I think. But the important thing is that this is the setting whereby children learn their first language. It is multimodal, it is incremental, and it is spoken dialogue. Multimodal means it's also co-located. The two people who are talking to each other are in the same physical space, and they can share attention with the same objects. So I've done some work there. That was basically my PhD. But along the way, my mainstay was this thing right here, the language understanding component. And to be able to put the object information and the language information together was an open question that I was working on throughout my PhD. So what is the meaning of the word red? I asked this question to my students in my natural language processing class. There's some of them are graduate students, some of them are undergraduate students, and no one has ever given a moment's thought of what the meaning of red is. And the answers are always vary, but it's usually something like, well, red is a color. Okay, that's a category. Green is also a color, but clearly red isn't the same, doesn't have the same connotative meaning as green does. So what is the meaning of red? And they usually work out something like, well, it's what you see. It's something that has to do with your vision. And that's true. There's something to that, right? If you understand the notion of redness, you have to actually be able to see red things and hear them called red. So, and that's kind of how humans do it, I suppose. Here's 4 red objects and someone says red, kind of around it, and red, and you see these objects and you hear this word, and your notion, whatever your connotative meaning is in your head of redness, gets stronger as you hear these and use these. So if that's the case, we need to somehow link perception to language. And this is the well-known symbol grounding problem. You may have heard of this paper that was published back in 1990. So, 30 years on, and this hasn't been solved yet. Progress is being made, but so my own contribution to this kind of area was in a 2015 paper called the Words as Classifiers model. And the model is embarrassingly simple, and it makes some terrible assumptions, but I think it's a useful illustration of the symbol grounding problem and how it could be solved, or at least one approach to it, where we represent real objects as low-level features. For example, use OpenCV or some software package and extract features from an object in an image, like RGB values, skewness, rotation, XY coordinates, stuff like that. Or you can pass these images through a convolutional neural network. And these convnets have been trained on millions of images, and they do have labels, but we don't care about the labels. We kind of ignore that, and we take a lower layer of it and basically vectorize any object that we get. And that vector represents the object. And I'm okay with that. I think that's okay because pre-linguistically, children look at objects and play with objects and do stuff with objects a lot. So they have this notion of affordance of objects before they start to learn denotative words to those objects. And I'm kind of, at least theoretically, I'm allowing myself to use pre-trained convolutional neural networks to represent objects. But then each word in a referent expression, or really in a corpus of referent expressions, has its own binary classifier. For example, there's, and denotation is, theoretically, the denotation is the objects themselves. Connotation is the classifier themselves, like the coefficients even. That is, the classifier returns higher probabilities for prototypical representations. For example, the red classifier gives higher probabilities for redder things. So here's how this works. So if we go back to kind of our holistic semantics and we focus on grounded, I have a classifier for the word red, and pick your favorite linear classifier. It doesn't even have to be linear. It could be anything you want, but let's say it's a logistic regression classifier for a moment, which is not unlike a single neuron in an artificial neural network. And sigmoid function, but it has all these coefficients, 1 for each feature. And let's say there's, I don't know, 1,000 features that come in. All you have to do is pass it examples of things that are called red, not ontologically red. I don't know anything that's ontologically red, or even if red is part of our ontology, whatever that is. It's more find things that someone called red, because that's all we got. So here's something that was called red, here's something that was called red, here's something that was called red, here's something, and give it as many examples as you'd like. And it also needs negative examples, because it needs to tell the difference between things that are red and things that are not red, or rather things that are called red and things that are not called red. And it gets to this. So at the end, we have a trained binary classifier that if I give it a novel object that it's never seen before, it can give me a probability of its redness, fitness, as it were. It's kind of a fitness score of red things. But if that's the case, if we can do that with colors and any other word that has connotative meaning that links to the visual world, what about other words like the word point? For example, I can ask you to close your eyes and make a thumbs up or make a point gesture with your hand without looking. And that's kind of remarkable. You don't have to stare at yourself to do things. There's something about your muscle memory that is also linked into language. So we looked into this a little bit. I had a student who was interested in soft robotics, and he had this thing he did with at Carnegie Mellon for a summer, and he came back and had this software package that had these kind of rough virtual hands, and you can see these lines in here are virtual simulated muscle activations, one for each finger. So the higher the number, the more curved the finger is, the more tight the finger is, tight the muscle is. And we generated several hundred of these images and put them on Mechanical Turk and asked the people to describe what they see. And they would say things like, well, it's a thumbs up or it's a point. So we had these descriptions and these these simulated muscle activations and these images, and we tried a bunch of different configurations using some grounding in this words classifiers model. And in some cases it was a neural network. And we found that having the muscle activations helped in a retrieval task. So there's something there. It doesn't just have to be vision, which a lot of natural language processing focuses on right now. And there's lots of modalities, take your pick, smell, tactile, auditory, haptics, and other people have worked on these. And so does holistic semantics / understanding require, to me, this lends itself, does this require embodiment? This is a question I don't have the answer to, but I'm kind of taking it as maybe. So I've read some books on this. There's Mark Johnson, who's of course affiliated in many ways with George Lakoff, makes the case for embodiment as a requirement for meaning and understanding. There's DePaulo's book, Linguistic Bodies, written by DePaulo and a couple of other authors that came out more recently. Language is embodied and language is embodied and inactive. You can't have a brain in the vat, as it were. Embodied cognition is a research field that I'm sure you're familiar with. And there's evidence for it and evidence against it, I suppose. I'm sort of taking it as maybe it's the case. So let's say for the moment that embodiment is necessary for holistic unified semantics. But if that's the case, I need a body to put my systems on and test them. And so I decided to start using robots. So I wouldn't say I'm a roboticist in the traditional sense. Roboticists build robots themselves and add stuff to them and care about actuators and electrical impulses and things like that. And they're more mechanical and electrical engineering, whereas I'm more of a consumer of existing robot platforms, and I want to put my systems on them and try them out. So I've purchased some robots. The first one I purchased was this because I was new and didn't have any money, and this only costed at the time about $250, and it had a Python software development kit. So I could record, I could take its sensory input from like its internal states and its camera, and use that as input, and then I could control it. Same thing with this robot, and this is a tiny robot. In fact, I have one right. Well, this is a vector robot, but it's no bigger than this. I would say 8 centimeters tall. And then there's these MISTI robots, which are a good 45 or 50 centimeters tall. And then I have this one's kind of fun, but I don't use it so much. But I have these robots, and robots are great because they're fun for students to learn programming on and things. But the moment you decide to put anything on a robot and put a human in front of it, you have problems. And it's the human-robot interaction problem, the HRI problem. And that is that humans anthropomorphize robots no matter how they look: gender, social norms, categorizations, intelligence, sympathy, et cetera, et cetera. So we had this Cosmo robot, and I handed it to a student, and I said, let's do a first language learning setup on this with an incremental multimodal spoken dialogue system. And my student said, okay, but if setting is important and humans anthropomorphize robots, then will humans anthropomorphize Cosmo in the right way? That is, will they treat it the right age? Because if they are confronted with a robot and we say, teach this its first language, and it looks like an adult, they're not going to treat it like a child. They're going to treat it like an adult and have these expectations of it. So we actually did a study on this, and I won't go into details, but we had this Kabuki robot with a Microsoft Kinect and the Cosmo robot in an unembodied dialogue system, and we had put people in front of them and had them interact with them, and asked them what age they thought they were. And Kabuki was an adult, the unembodied dialogue system was an adult, and Cosmo was a small child, no matter what setting we put it in, because we wanted to establish that people treat Cosmo as, kind of preschool toddler age, and we at least found that. But that was an interesting outcome, that people anthropomorphize robots for age. And that's something we have to control for when we ask people to do certain things with our robots in certain settings. So that student graduated. Another student came along, and I handed that student Cosmo, and I said, look, we want to get a multimodal, incremental spoken dialogue system working on Cosmo with this words as classifiers model as the language understanding component. And we know that it's the right age. People will treat it the right age. We know that, but we can't obviously have it talk in full sentences. We have to have it start off really small. And my student said, okay, great. So he takes Cosmo, plays with it, and he says, well, wait a second. If the setting is important and humans anthropomorphize robots, then will humans interpret Cosmo's actions as if Cosmo is displaying some kind of emotional display? For example, acting curious, frustrated, or angry. And I thought, does that matter? But it turns out that Yekaterina Novikova in her 2015 and 2017 papers said, you can't get away from it. You can't avoid it. If you put a person in front of a robot and the robot does anything, if it's just an arm and it's doing this or that, if it's a Roomba and it's driving around your living room vacuuming, they're going to anthropomorphize it for emotion. They're going to assume it's producing emotional characteristics, even though they know good and well, most people know good and well, they have no emotion. So we needed to kind of figure this out. So what we did was, Cosmo was nice because it has over 900 prescripted behaviors. You can just invoke them, and they run between 4 and 10 seconds. Something like it lifts its lift up, it turns left, it does something with its animated eyes, it makes a noise.
Casey, can I just make one request? Half of the audience is not their native language isn't English. So I ask you, please speak not as if you're speaking to fellow people from Boise, but to not to child robots, but to people who don't speak English as a first language. More slowly, okay?
Okay, I can do that. Yeah, thanks.
And the second thing is, could you define anthropomorphize?
Okay, so anthropomorphize is, I mean, think about Disney cartoons. In a Disney cartoon, you have an animal that speaks. So adding speech to something is a way of anthropomorphizing it. It makes it seem like it's more human. And giving animals or giving them emotions makes it seem like more human. But when a human looks at a robot, and the robot has human-looking characteristics like eyes, or it has a voice, people anthropomorphize it. They assign human characteristics to it. And robots move as well. And when robots move, it seems like their movements are human-like in a way that they assign emotion to it. So what we did with Cosmo was we recorded all of its prescripted behaviors. And we put them on, again, on Mechanical Turk, and asked people to label them for what the emotion they thought Cosmo was making. And we also had them describe the behaviors. And the labels they came up with were interesting because they were very different from what the designers intended. Like if a designer intended a happy display of emotion in the robot, someone might have thought, well, it looks kind of sad. And we were able to model this. We were able to take the robot inputs or stuff from the robot, like its face, its audio, and its internal states, its movements, like its lift height, its left wheel turn speed, those kinds of things. There's a whole bunch of these internal state variables. And we can take those and pass those over time as input to a model. In this case, it was a neural network. And we were able to predict the labels, the emotion labels. So, and that's kind of an interesting take on this, I think, because we're not looking at the human and looking at the human's face or asking the human what they think, what their emotional state is. We're asking the human to consider what the robot's emotional state is. And we're able to predict that, what a human would think the robot is what emotion the robot is experiencing. And that turned into a couple of publications. And I'm going to actually skip this. Okay, so we've done some work here in human-robot interaction to kind of get at, make sure the setting is right, because it has to be spoken dialogue. It has to be co-located. Robot and human are in the same place. We have to control for a few things, age and emotion perceptions of the human on the robot. So with that kind of control, now we actually need the system to put in there. And I just want this as an aside. I've spent a lot of time architecting spoken dialogue systems that are robot ready. And these are some requirements for that. And these might be interesting to a cognitive science community, because they're kind of requirements that come with us as humans when we're born and as we develop. The incremental processing, for example, it's continuous input. Full duplex means I can never turn my ears off. I have to be listening all the time, and robots need to have that capacity as well. There's a lot of different modules that need to talk to each other. So they need to, and the modules, like something's doing the speech recognition, something's doing the language understanding, something's doing the talking, something's doing the movement of an arm or a wheel, and those need to talk to each other. Temporal alignment's important too, because I have a modality coming in my ear and I have a modality coming in my vision, in my eye, and those happen at the same time, and those times need to be synchronized. And that seems obvious, but in robotics or in multimodal dialogue, the speech recognizer might have a 350 millisecond delay and the gesture recognizer might have a 50 millisecond delay. And that will cause problems with when things happen for the understanding. And we need lots of sensors and planning and generation and realizers, like for speech or extending an arm and putting it in a certain position to point at something. And I've done some research on this, and we've built our own dialogue systems for this that we can get working on robots. We have a demo this year at SIGDIAL, which I'm pretty proud of. But the thing about this field I'm in computational linguistics is we do actually have to build these things on the robots, and they have to work, because if they don't work, we can't test our theories. So I finally got to the point where my student finally was able to put Cosmo in a room with a person. Cosmo had a multimodal, incremental spoken dialogue system on it that was using the words as classifiers model of grounded semantics as its language understanding component. And he was able to get it to learn some words as it interacted with very few examples and in a very tight interaction. And it was an amazing thing to watch. Cosmo was constantly moving. Its arm was moving up and down a little bit, and we moved left to right, never held still. And his research question was, can emotion help overcome the cold start problem of language learning? That is, children don't have words to use to learn words. So the first words they learn are really crucial. And the first kind of steps of that process, of that developmental process, is very crucial. And our assumption or our theory was, we've seen in research that there are other things that can facilitate language learning for the first language. And one of those things obviously is gestures and pointing and other nonverbal things. But the other nonverbal thing that hasn't really been considered in robot interaction is emotion. Can the use of emotional displays of behavior signal understanding and confusion in the language learning task? So there are only two emotional states that were displayed in a behavior, not with speech or anything, but in a behavior. So understanding. So an understanding display in Cosmo might be like, it goes up to the object, looks up and down kind of at it, and it kind of does this happy hop. And it's like, okay, I get it. And then confusion might be something like it narrows its eyes a little bit. And we didn't invent these behaviors. These were ones that were prescripted, and we tested to make sure that they were labeled like that. And it turns out that it did help. We had kind of an A/B test where we had the system learn without emotional displays and one system that learned with them. And so even though time was taken to display emotion, there was much richer interaction and there was better learning when the emotions existed. So it's important for our robots to display emotion, but the emotion importantly has to be the right emotion, and it has to be novel. And that was some recent work that we published. So all of this was all about just getting the setting right. The setting is important. And that's, I think the reason why I'm bringing that up is because in the distributional semantics, like embeddings, word-to-vec, BERT, those kinds of things where they're all trained on text, there's no setting there, it's just text. And I think they're missing something when they do that. But in order to get the setting right, all of this stuff has to be in place. You have to have an incremental multimodal spoken dialogue system. You have to actually build the thing. It has to be put onto some sort of a body. It doesn't have to be a robot, but I decided to put mine on robots. And when you have robots, you have to control for the anthropomorphization of human-robot interaction. And finally, now that I've got the setting right, I'm returning a little bit, well, kind of in parallel back to this model that I have, this words as classifiers model, which is clearly not adequate enough for handling all the crazy things that happen in language and to holistically learn and represent meaning. So I want to come back to this, kind of push formal semantics aside. What if there's a way to bring distributional semantics and grounded semantics together, unify them as it were? So if I take my model of grounded semantics, my words as classifiers model, and I train a lot of these, like say a vocabulary of 1,000 words, red, green, blue, up, down, those kinds of things. And so I have an individual classifier for each word and I have images for all of those things, positive and negative examples. What I can then do is take these coefficients out of it, which is what was done for WordDev at the beginning. And these coefficients are a vector. So I can take that vector and concatenate it, put it together with the distributional vectors for the same words that were trained on text. So I can take the vector for my red classifier, which was trained on images, and the vector for my distributional semantics model, which was trained on text, and I can put those together to have a kind of better representation of meaning that is kind of both abstract and concrete, one that is trained on text only and one that is trained on images only. And we looked at this a little bit. You can take these high dimensional vectors and you can project them down into 2 dimensions and cluster them. And we found that these words that were trained, like parked, forward, vehicle, pickup, were all clustered together. So you see these vehicles that are close together. And then you see cat, dog, horse, cow, those are all clustered together. So animals are kind of over here because of the way they look, because this is all trained on images. And then there's prepositions here, and there's colors here, and there's things that kind of extend from the arm here, and there's kind of this big cluster in the middle that's sort of all kind of there and hasn't been really teased apart. But the interesting thing about this doesn't really prove anything, but the interesting thing about this is that we can take visual information and represent it as a vector and put it together with other vectors. And that's a student of mine did that for her master's thesis and came up with some interesting results. And there's some other people working on that right now. But this made me think, if it's the case that we can take all of the animal classifiers like cat, dog, horse, and mouse, and they cluster together, that must mean there's something about their coefficients, these things, that are similar to each other. So this kind of made me think, what if we took things that are category in the same kind of category, like colors? Let's take the classifier for red, train it, get its vector. Let's take the classifier for green, train it, get its vector. Let's take the classifier for blue, train it, and get its vector. And let's do that for lots of colors. Can we then train a classifier for the concept of color? Same kind of setup, same classifier, but instead of pointing the features at like images, like we've done with color classifiers, instead of that, we actually pointed at these vectors. So these inputs are from the coefficients of the classifiers instead of the images directly. And to me, this may be at least one level of abstraction. So in this case, red, green, blue, these are concrete words because their meaning is very well grounded symbolically. These are the symbols, and then the meaning is grounded into the visual world. But then we have the word color, which is kind of abstract, but kind of concrete in that color is kind of just a grouping of these kinds of words. But it's the first level of abstraction, I would say. All of these words are a color. And this color concept could be learned from just various different color information. But I think there's something theoretically pleasing about not having it look at images, which is what these are supposed to do, but rather having it look at what the images, what these learned. And what they learned was their coefficients. So we can give it positive examples of color things like red, blue, and green, and negative examples of things that aren't color, like zebras and ponies and computers. and it can distinguish between colors and non-colors based on the so I've spent some time there, and I'm getting towards the end of my talk, and I've gotten to this point, but I did want to mention that this is still a very wide gap. Even though this has taken me a good 10 years to get to this point, there's still a lot left, and there's still a lot more that obviously I'm not doing that I should be doing. There's a lot of assumptions in my semantic model. There's a lot of things I'm not doing in the robot and the dialogue system, for example. And there's a lot of other fields who are contributing to holistic semantics and getting at understanding. But there's still, this is decades in the future, I think, for holistic semantics. And some open questions I have to finish. Would a more playful robot facilitate language learning? So I have to always ask these questions about, is the robot doing the right thing? Is the setting right? Because the perceptions of the human, that is their anthropomorphization, the way they look at the robot and their expectations they have of the robot. Are we getting all of those right? We've already controlled for age, we've controlled for emotion a little bit, but we know that children play a lot, and that probably lends itself to language learning because they're experiencing the physical world more actively, more intentfully. And it's also a way for children to interact with others and to get people to buy in, to help each other, I guess. Can children learn, next question, this is very different. Can children learn abstract concepts without first learning concrete concepts? Do all abstract concepts eventually ground into concrete ones? And I know that, Stephen, your paper, or I guess it was a book chapter, to abstract is to single out some subset of the sensory input and ignore the rest. If you take a very abstract concept like utopia and you kind of recurse down on its meaning, as it were, you finally get at the percepts, you could say. And I know a lot of people who believe that. I don't know how to show that in computational linguistics. One thing I have done recently, just to kind of test this, is I've taken a dictionary, and so words and their definitions, and I've taken that and aligned that with age of acquisition data. And you've heard of the age of acquisition data set or corpus. So the age of acquisition is, I have words and the rough average age of when those words were used by children. So if I have that information, I kind of know when children learn words, roughly, at least English words. And I took that and I took all the words in my dictionary and got the average age of acquisition age for those words. And then I took their definitions and found all of the age of acquisition words for those and averaged all those together. And there's a difference. The definitions are much older. Sorry, the words are much older than the definitions. It means that words are defined by words that are learned younger, which makes sense, but it hasn't really been shown in my field empirically. And I think it's important to show at some point because of distributional semantics makes these kind of abstractness assumptions that there is nothing to ground into. We don't need to. Next question, should we use pre-trained language models for the first language learning tasks? Kind of like I did with the pre-trained object recognition models, even though they were trained on adult written text. Is that fair? Is that kind of baking too much, I guess, language instinct into the system before you even start teaching it words? Does it make sense to bring together formal distributional grounded semantics? If yes, then how? That's kind of my current idea, but I'm not sure how to do it. And there's people who are working on certain subsets of it. And can we arrive at fully intelligent agent that has no emotion? I think my recent adventures into emotion, which has only been about 3 years now, has really made me think that emotion has an important part to play in intelligence and in language, that the two aren't separated from each other. And I mean, I've watched Star Trek and I've seen Commander Data, and he didn't have emotion, yet he was this fully intelligent agent. And I think that we kind of think about intelligence that way. And I've read some books recently that are published recently that say emotion has nothing to do with it. But then the more I read about cognitive science, certainly about embodied cognition, emotion plays an important role. So that's an open question, for me at least. That's it. That's what I've been doing, and that's my research, and I'm happy to take questions and discuss.
Thanks very much. Could I ask everybody to turn on their faces now? And I think the way we, once we have enough faces, can we have the faces on? Si vous n'avez pas compris, c'est ça, continuez. I don't know if you're aware of the new convention in Zoom land. We can't applaud because it produces too much noise. But the way you do it, and I'll give a signal 1, 2, 3, and then you do it, is like this. It has the same effect. Okay, 1, 2, 3. Thank you very much.
Wow, that's great. That's better than
now. The floor is open for questions. Here too, I suggest that because motion, the eye is more sensitive to motion than to statics. If you have a question to ask, don't use the computer. Just go like this with one hand, and I'll recognize you, and you can ask the question. And yep, Maul.
I do have a question.
Maul, go ahead.
Yes. You were explaining about the first level of abstraction and how to combine vector and grounded together, for example, to find the meaning of red. My question is, how about the other level of abstract words, like, for example, sadness, happiness? Did you work on this part as well?
So, not as much as I would like to. We do have a paper in SEMDAL this year. It was actually one that I skipped. I'm going to share my screen one more time. Since you asked, I will bring it back up. It's got to go back here a little bit. Actually, let me just find it. So we did this research where, since we had this model of mapping from robot to emotion, we decided to take that model, which was a distribution over 16 possible emotions, and actually ground descriptions into it. So kind of, yes, to answer your question, we've kind of looked at this. We had these descriptions of the robot behaviors, and we had this model that could take robot behaviors and come up with a distribution over the emotion of what the robot is, well, at least the perceptions of the robot, the human perceptions of the robot's emotional state. And we took descriptions and did symbol grounding into that, as well as the robot states. And did that, use a retrieval task use that information for another retrieval task using descriptions, and got some better, the results were better when we had some notion of emotion in there. But then we kind of looked at some research that shows that, I mean, this is Barrett, what's her first name? Kind of positing that emotions are—
Lisa Feldman.
That's the one, yeah. Lisa Feldman Barrett, her book on emotions, how they're actually very tied to the linguistic system, and there's the emotional substrates it's not as clear as it maybe once thought was. There's of course affect, and there is of course valence and arousal and those kinds of things, but the linguistic system is very closely tied to how we describe our emotions, and in turn how we feel them, I guess, or how they manifest themselves. So we also did, as a part of this paper, another thing we did was we took the descriptions and used distributional semantics to map them to the labels. And the comparison there was interesting, because we're going from description to labels in any case. And when it was done using grounding, or done using the robot internal states, it worked better, which means that maybe it means that they were more fundamental emotions, as it were. But, so we've explored this a little bit in the robots. Obviously, we can't make any broad sweeping claims because the robot doesn't actually feel emotion. This is just a model of perceived emotions. I hope that helps.
Matthew, you had a question.
Thank you.
Yeah, this is just a clarification question, but I didn't quite understand your experiment with the robot and what exactly the task was. So just to recap, basically you have a robot, you gave it a model of grounded semantics, And then did you get participants to interact with the robot and teach it new words, or?
Yeah, so, okay, so that's this experiment. Let me share my screen again. So in this experiment, yes. So I guess that wasn't clear. I kind of rushed through this. The robot was in this room on a table, and it had these objects around it. And we instructed my student instructed participants to help the robot learn. And that was actually their task. It was to teach the robot new words, because the robot didn't know any words. So it was really starting from nothing, and they knew that. So they would sit down at the table, and they would. I wish I had a video to show, but my student didn't get back to me in time. So these objects were here, but they were allowed to use any objects they wanted. So like someone would put an object like this in front of it and say, "Hey Cosmo, this is red," and it would hear these words, and it might hear in another context, okay, red or orange or green or L-shaped or big or small or left or right or something like that. And they were free to use whatever words they wanted, but their goal was to get Cosmo to utter the words and utter it in the right context. So Cosmo would hear enough examples of the word used, and then it would propose the word. It would say, red. And they would say yes. And if they said yes, that means Cosmo learned the word. And if they said no, Cosmo didn't learn the word. So we kind of baked in added a lot of kind of scaffolding to it to have the interaction work, even though the thing we were really trying to ascertain was, does emotion, turning emotion on, help facilitate the robot's language learning? Does that help clarify it? And we had about 21 participants come and interact with the robot, but each one was independent. So Cosmo could have learned 5 words with participant 1, but we kind of had to throw that away, and it could have learned 10 different words with participant 2, and so on. So they all had the same starting point.
Okay. And
Well,
so,
whoops, sorry. Go.
sorry, so the dependent variable would be something like, how many words did Cosmo learn according to
Yep.
the participant?
Exactly. So that was the main dependent variable. There were some other things we were looking at, like just did they talk more? Was there more tight interaction? How many times did Cosmo propose a word? If it only did it once, then that wasn't very interactive. If it did it 10 times but got 8 of them wrong, it's not learning as well as it could be, but it's still interacting very tightly. So and that lends itself to people are buying in, and they're actually at least trying to help, even if the model didn't do a very good job. It does help us to know that the setting is working. But the main dependent variable, you're right, is how many words it learned. And we defined a learned word by Cosmo proposed it and got a positive response from the participant.
Okay, Mao is wiggling her fingers again.
Thank you. I was wondering if you had the capacity to change the voice of the robot and to teach it more complex movement sequence to show a sort of growth that is more culturally recognized or even intuitive.
That would be great. We haven't gotten to that point yet where we need to. And right now I only know of 2 settings. One is Cosmo's voice, which is kind of this cute, young sounding voice. And then if you turn that off, it's this adult male strange voice that it really does sound strange coming from that robot when you're used to its other voice. But I know that you can set parameters and change the contours and stuff like that. So maybe as it learns, that happens. But that's precisely part of you're absolutely right. That's part of the setting. If it knows a certain vocabulary, it should be at a certain developmental level. And if it's at a certain developmental level, its voice should reflect that. But then its size should too, maybe at some point. That's why we have multiple robots, but that's a tough thing because robots don't grow. Yet we want them to go through the learning process from childhood, from pre-linguistic on, and that's very difficult unless we have something that's also kind of physically developing. I mean, that's a really good point.
Okay, Friedemann has a question. Friedemann Pulvermüller. Let me point out also, before I present Friedemann, that there are several people who are in this series who are watching and who will be speaking later. Friedemann is one of them, and I cede the floor. Welcome, Friedemann.
Yeah, thank you very much for inviting me and also for your very interesting, exciting talk. And it's a nice thing to have such a worldwide seminar.
Yeah.
I appreciate this. Right. A very interesting talk, as I said. Could you tell us a little bit more about the neural infrastructure of the robot when he learns the correspondence between a word like green and specific patterns? Is this kind of pre-wired in a way, or would you hand wire those links, or is there a learning rule, or how do you do that?
Right. It's embarrassingly minimal or simple. It's more like, it's almost like we're taking an individual neuron, artificial neuron, and training it on purpose without kind of putting it in a larger network and hoping that it picks up some regularities. So we take a classifier, like a logistic regression classifier, and we give it a bunch of examples of red things and a bunch of examples of things that are not red, and it learns the difference between the two. And we do that systematically. You can do that with a corpus, but the way we did it with Cosmo is basically we have a way of, if Cosmo hears a new word from the speech recognizer, and that's assumptions in that too, that the speech recognizer does its job perfectly before we start using it. But we're taking these symbols from the speech recognizer, and once we get one, we create a new one of these untrained classifiers.
Mm-hmm.
And then as Cosmo's interacting with the world, it's taking in images all the time. But it hears a word, and when it hears a word in conjunction with seeing an image, say in a window of 5 or 10 seconds, then it adds those to the list of positive examples for the word that it heard. So if it hears the word red, it's going to take all the images that happened, and it's doing this, I think, 4 or 5 frames per second. So it's going to take 15 or 20 frames. Hopefully there's a red object in there somewhere, and it gives that to it. And then it samples from negative examples from just anything that wasn't called red in its memory. So we keep track of all of these images. And then at intervals, it trains these classifiers. It is a supervised learning, a supervised classification problem for each individual classifier.
Yeah, but on the other hand, you make it the comment now that if you predetermine your system to develop a classifier for red, or then also for color, for demography, whatever, it's not so surprising that you finally come out with a result, and there's indeed a set of visual perceptions that relate to the abstract concept. So that's kind of what you put into your system. You don't explain.
So
abstract concept, for example.
Right. So maybe if I clarify that a little bit, we don't actually give it a vocabulary beforehand. It doesn't know any words, and we don't tell it which words it's going to learn, or it could learn.
Mm-hmm.
That all comes from what the participants say.
But the classifier is predetermined.
The fact that it's a logistic regression classifier, yes, it's predetermined, and we will assign every word to a logistic.
You do not have the word green, but you have a green classifier.
No, we have no classifiers at the beginning, but when it hears the word green for the first time, it creates a classifier for that word, and then starts collecting visual information that corresponds with it. So it's at a level of really. It's not at a level of abstraction. We're assuming that all words are concrete, and that's not a very good assumption. And we're assuming that all the words that they're going to hear is going to denote something in the physical world, and that's also not a very good assumption.
Okay, could you speculate about how you could make this architecture more biological? So how?
I wish I could, because I don't know enough about biology to try to make it more biological. Right now, I'm just trying to get the setting right, because if someone works on the biological representation, and people are, although when they claim they have a biologically inspired neural network, it's always not quite clear. I think it's dubious in a lot of cases, especially in natural language processing. So I'm not making any broad sweeping claims that what I'm doing is the most cognitively plausible model. That would be great if that model exists, existed. What I do think I'm getting right is the setting, and I'm trying to get the behavior right. And then once that's kind of all in place, then the putting the right model in is, it hopefully works better, I guess, than if we just give it text. This model obviously isn't the right model.
Yeah, thanks. Anyway, it's a good attempt.
I know
Thank
it
you.
doesn't. I know it doesn't make you happy. Maybe we can talk some other time. I know that your talk is coming up in a couple of weeks.
What
So.
makes you happy finally?
Didn't you say that you were also interested in using convolutional networks?
Well, that's where these are coming from. So we actually pass all of these. Oops, I got to share my screen again. I'm pointing at something that you're not looking at. So these images that we give to it, we represent them vectorized as convolutional neural network output. So every image that comes through Cosmo, that gets passed through a convnet, and we take its vectorized output, and then that forms the input to these logistic regression classifiers.
Okay, which database did you use for the age of acquisition? Could you unshare? Yeah.
Oh my goodness, which one was it?
Well, either it was the Briesbart series or the much smaller but production.
It was the Briesbart one, yeah. It was like 32,000 words or something like that.
Okay, and what was the difference? What was it? You mentioned something about concrete and abstract words early.
So yeah, so the words in the dictionary, not their definitions, the words in the dictionary, if you pass those through an average over all of those, the average age was about 11 years old, according to age of acquisition. Of course, it didn't have all the words, but the words that it had were age 11. And these, I think age of acquisition goes up to age like 35 or something like that. Whereas if I take all the definitions and get their age of acquisition, average everything together, it's age 6. So at least for the ones that it had, the words are defined by words that are learned earlier, or rather younger in the age of acquisition data set for sure.
Marcos, do you have anything to say about that?
There's some questions in the chat too.
Well, no, just think this is the most practical option. I'll start off with that too.
And I mean, I'm trying some other things, like WordNet has these ways of connecting words together, and you can kind of take a word and find all the words that it's defined by or that it's connected to, and find that words that are connected to it are lower in the age of acquisition scale. I've also taken the BERT model and kind of given it a bunch of words from age of acquisition and said, okay, if I have a word in BERT, a vector, what are the closest 10 vectors, and get their age of acquisition and figure what the average age of acquisition is for words that are defined by other words. And those are lower too, not by as much, but there are lower. So even BERT and these embedding models pick up on those kinds of regularities, but I'm still not sure how to, it's not ready to publish yet. I don't know how to tell my colleagues in natural language processing, which is this huge growing community, that BERT is missing something. And it might be good for our community to consider abstract versus concrete and other ways of thinking about, the progression of learning language and the meaning of words. And you're losing something when you only pull it from text.
Okay, so you saw some questions in the written version. Are any of the people who posed their questions in writing prepared to say them orally, or should we treat them in their?
I can.
Go ahead.
Tama, it's pretty short question. It relates to an earlier presentation we had by Fritz Kunter that was very interesting, and somehow queuing on the same concept and same exploration of semantics and joining multiple signals. And there was one thing he told us that was very surprising. All of his abstract concepts were classified, actually produced images of human faces. His deal was not exactly like you using robots, but was the same principle of using, on the one side, a pre-trained model done with text and then joining with images. But this time the neural net was supposed to tag with images, giving the closest image from the cluster, and everything it got from everything that was abstract were image of human faces. So that was fairly interesting. That rose a lot of questions. You didn't know why. That was something to explore. So I just wanted to point that to you. Maybe you have an idea or a way to investigate how do we build abstract concept, because when we use those strategies of mixing with word classifier, it gives some special results, like abstract is all about humans.
Yeah. So I don't have an answer to that, why the human face comes up. Maybe, I don't know if it's related to this. I was reading a paper, I think last year, and it was the first time I was confronted with the idea that, I mean, when I thought about emotion and language, for example, I always thought emotion was physiological, it's chemical. So the emotion is a pre-linguistic, it's a substrate of our cognition. And then I started reading, I read a paper that looked at connections between words and emotions. And they found that abstract words ground into emotions more than concrete words do. So at least when they're used abstractly. So like democracy and utopia have emotional underpinnings, I guess, at least, or emotions are more tied to the linguistic system than we thought. And that's why I read Lisa Barrett's book, because she tries to make the case for that in a kind of a, I guess, upending the whole field of emotion, understanding what emotion is. But I'm just interested in how it interacts with the linguistic system and what the theories are out there. And that one blew my mind. And I don't say the word blow my mind very often, but that one did, because I thought that emotion was pre-linguistic, and here it is kind of not. There's these abstract words that ground into emotion. So it might have something to do with that. I don't know.
Thank you, interesting.
Yeah. If Francis, do you want to ask your question out loud, or should it be answered from the written version?
Well, it's the same out loud. I was thinking about the research. First, thank you for your great presentation. It was very nice. Very enjoyed it. And secondly, I was thinking about Mr. Arnard's research on the minimal set of words from which the meaning of all the other words can be constructed by definition. And it would certainly be interesting to start with this set of words for your robots.
So I think this is one, and I wrote this down, I copied this out. Thanks for adding that. And I think that's wonderful. I remember talking to some fellow students once in Nancy, actually, and one guy was really interested in formal semantics, and he was all about lambda calculus and thought it was the best thing. And I said, well, what are the fundamental concepts that we can build lambda calculus on top of? And he said, I don't know, those don't matter. And I thought that it was actually a really important question. So this is kind of a nice starting point. So I will look at those. Thank you. So
I have a question about that. So you're not familiar with you cited that 30-year-old paper, that's fine, but you're not familiar with the dictionary work that we're doing here.
No, that's new to me.
Okay.
And in fact,
I urge you to tune in when Marcos gives his talk, because he'll be making some reference to it as well. Are there other questions? I have a few, but I want to wait till you've asked your hard questions so I can ask my easy questions. Arthur, do you have anything to say? We need your speaker.
Thank you, Stephen. Well, first off, it was a very nice talk, Casey. Thanks. And yeah, I also saw the relation to Fritz Gunther's talk. And so, yeah, the two of you might get together on some of these things. The one thing that I wanted to point out is for people like me and Friedemann, one of the components of meaning that you haven't incorporated yet is action. You know, how we interact with things. And so as a child is learning about a ball, it's not just learning, you know, that it's white and it's round, but but how to hold it and how to
Yep.
throw it, and the dynamics of their body and the dynamics of the change in the visual situation that happens from their action. And my guess is that an important component of meaning are the implications for action. So the meaning of a situation for me as a human with my sort of body, the meaning of that situation is how I can act in it. You know, how maybe I can get food, or I can walk, or I can play, or I can communicate with somebody. And that notion of action, or to take the Gibsonian idea of affordance, that's not there yet. And it would seem like be an important thing to be considering.
Absolutely. I would agree with you completely. It's missing and it needs to be there. We have done a little bit of work on verb learning, where the state of, like, the robot moves its lift up. So there's kind of these state changes, and the verbs kind of ground into that. So we've kind of moved into that direction. But all the stuff with affordance, cause and effect, how are my actions tied to language, those kinds of things is all stuff that's on our list of future things to look at. And there are other people looking at it. And I do realize, and I'm fully aware that the way our model of words as classifiers model is formulated is insufficient to capture all of that. It needs to be enriched in a lot of ways. But yeah, I fully agree with you.
The first point at which that's saying, there we have Friedemann, go ahead, sorry. Friedemann, turn on.
A mini comment here. You mentioned verb learning. However, the point art might apply not only to verb learning, but also to abstract noun or abstract word learning.
Yeah,
Take
I
the
agree.
example of point, which you mentioned. Now, point, what is it? In mathematics, we say it's not. It's just a single unit of space of space. Not zero extension in all three dimensions. But this is probably not so compatible with language use. A point is something you can point to usually, and so the pointing action is kind of very important for learning this abstract term.
This is great. I need to talk to cognitive scientists more often. I don't get. I agree. The abstractness and the verb stuff, that's been kind of pulled out of it. Yeah, and I mean, you've done this, right? Your 2018 paper, I actually have it in my Mendeley here, abstract semantics in the motor system. This is the stuff I read a lot to try to gain inspiration, but it's not always clear how that makes it into the robot and actually works. That's a tough thing that we're trying to work on. But yeah.
Right. Yeah, we have done some work on exactly that. We once had a European project with a few centers, and there have been even robots developed by neuroinformaticists like Stefan Wörmter or Günther Palm. They published over 10 years or so bio-inspired robot stuff. Also, Angelo Cangelosi does very exciting work in this direction.
There's a group in Bielefeld that does bio-inspired robots.
Cangelosi has a model of abstract action-related semantic learning on a robot.
I was going to invite Angelo, but we filled up too quickly and there was no room, but maybe in spring we can invite Angelo as well.
Right.
Very good. Okay, there was a question from Pierre Vadnet.
I have to say goodbye, I'm sorry.
Okay, thank you for coming, Friedemann. See you again soon.
Bye-bye.
Oui, bonjour. Casey, I must say that I loved your research project. Maybe it's because I've been asking myself the same question for the last 15 years. And at this point, I got thinking that maybe the most anthropomorphic part of learning anything comes from the vital need that humans and animals have. And that vital need represents some necessity. Your robot doesn't have any need, and there is no way that you can put needs there that are robots' need. They will always be human needs. And then you are back to anthropomorphization.
Right.
I don't know. At this point, what I find out is that there are two different levels in learning. A basic level, which is at a causal level. At some point, you talked about the cold start at the word level. But the word level is not really at the basic causal level. The word level is different because it is a symbolic level. And to me, these two levels could be defined as symbolic and non-symbolic. And the symbolic has to be grounded in the non-symbolic, but the non-symbolic is learned in immediate and exactly what you're trying to do with your robot. Put the robot in a certain environment where another person is there and provides things to learn. Even if there were nobody there, the robot should have something to learn, but because you don't have a need in there, your robot is not trying to learn without being stimulated.
Right.
And then, of course, it depends on the how much stimulating your environment can be. You
Right.
could change the environment, have many robots and things like that.
Okay. Very good points. Very good points. I mean, that was actually one of the first things my student was concerned with. He said, okay, if these he didn't pose it quite the same way you did, but if robots don't have needs, then if we bring a human into the room with a robot and say, okay, now teach this robot, what do they care? It doesn't have the same needs as the human does. It's not like it's a baby learning and it needs to function in the world. So his big question was, how do we get humans to buy into the robot and actually help it as a team, kind of teach it, which is why the emotion thing was kind of important. If it displays that will help them buy in. But of course, we're manipulating the human instead of actually putting the need inside of the robot. It's missing a lot. I agree. And there might be ways to simulate some of that stuff that would make it better, or at least make humans more, I guess, willing to help the robot learn. But that was also tied to the question I had at the end of is play important? So humans play. That's part of a kind of a pre-linguistic behavior that, and even ongoing, that humans do. And like anyone who's been in the room with a 2-year-old know that they talk all the time. Some children will just talk nonstop to themselves, to the wall, to their to their toys, whatever. And that's something that we can do with robots, is really give them kind of a reinforcement learning setup where just talking and just interacting is the thing that you're optimizing for. That's the thing the goal you're trying to get. And whatever you learn from that, great. So the need could be put into a reinforcement learning scenario, but you're right, there's no biological need for the robot other than it needs electrons to function.
Very good.
Okay. Is it possible that only the passive stimulation, the fact that you cannot shut your ears or you can close your eyes, but normally there is some part of the stimulation that is there and that you have to accept passively, and that the connection between this basic stimulation and the actions or the actuators, whichever they are, is it possible that this is built automatically, strictly randomly? Maybe one suggestion that I tried to look at some point, neurologists or people in neurology in general when they do experiments with monkeys and other animals like this, they set up their experiment on the basis that they try to teach a task to the animal, but in fact, the animal get the drop of juice, and that's something that you.
Pierre, it's freezing. You're freezing both.
And not to be useful.
Attention, Pierre, ça gèle. Faut répéter ce que tu as dit.
Okay, sorry. Must be my internet connection. Ce que je disais, c'est que what I was saying was that neurologists use experiments with animals, and they try to teach tasks to the animals. But in fact, the animals see the experiment more from the fact that they only what they want to do is get a drop of juice. Now, how can you build something like that into your experiment? Because maybe what the neurologists, in fact, they start from very basic things when they teach to the animals. It's about the same thing as making the difference between red, green, and blue. And we can do these categorization because we have sensors which automatically force the categorization. Some sensors catch only part of the light, the red, the green, or the blue. And then from there, you can combine the results to get the other colors. Now, I don't know. What do you think about copying the neurologists in their experiments?
I don't know. That's something to consider. I mean, it's like, and maybe that's what's happening anyway, because if we endow robots with some sort of a motivation, like in a reinforcement learning model, maybe the thing we're giving it is basically equivalent to it trying to optimize for getting the juice, whatever that is. But it's not actually, and it's learning stuff along the way to get the juice, but it's not actually getting understanding or getting learning real language, I guess you could say.
Okay, we've now reached the official end of the time, but I want to make the following proposition. Those who feel that it would be rude to leave at this point, it's not rude, you can leave. And that actually includes Casey. If Casey decides that he's had enough, then we'll call it off now. If not, we can continue a little bit longer, and I'll leave the tape on a little bit longer.
I can talk about this all day.
Okay, so feel free to leave. Mao had a question, and then I have a few too. Go ahead.
I was going to go in the same direction, but the notion of affordance seems somewhat skewed when you talk about a robot, because you can't ask it to grab the apple the same way that your human would grab the apple. And I'm wondering what kind of effect it would have on linguistic perception, given that we are sort of considering that our affordance hierarchies are what builds understanding to a certain degree. So once you give your robot a high level goal, a high level enough goal, it will then start creating understanding based on the affordances that allow it to reach that goal. And I was wondering if you were ever going to consider maybe a robot that, I don't know, had hands or something that looked less like a little toy truck, which is great, but it might really skew its perception.
Yeah, exactly. There's actually two parts to that. One is the affordance that the robot perceives, but then there's the affordance that the human thinks the robot has. And you're right, if the robot has a lift, they're not going to say grab. They're going to say something like lift the apple or push the apple. So the robot's going to not get all of the vocabulary that humans are going to get. But there are people working on that, though there are people working on grasping in robotics, but there are people who are working on something similar to where affordance is tied to the linguistic into a language understanding system, but it's mostly for navigation. So if I say a high level goal to the robot, go to this location, the robot has to determine which way to turn, if it needs to go around certain obstacles or anything like that. So it needs, at any given moment, it has to determine the affordance of what's around it. Can I get up on top of something? Can I move it out of the way, or do I need to go around it? Those are all things it has to do. It's kind of low level right now, but mostly it's avoiding objects so it can drive somewhere or walk somewhere. But people are working on that right now. Affordance is something that I wish I could spend a little bit more time on, and maybe I'll have to, because I'll be stopped in my research unless I do. But there are smart people working on affordances, thankfully, and moving those into kind of a semantic model. A former colleague of mine from Bielefeld actually is kind of doing that, pulling affordance from observing objects, for example. It's not answered. It definitely needs to be there.
Other questions? Yes, go ahead, Sweela. Turn on your mic. That's it.
Yes, thanks for your presentation. Je vais essayer de poser ma question en anglais la première. Je vais montrer.
Tu peux en français si tu veux, je traduis.
Ok, mais je vais commencer quand même là en anglais. Je vais m'entraîner quoi. Et la deuxième en français. Okay. In the final, if I understood correctly, we trained the robot to represent the semantic through donc a set learning factor, but it cannot understand, but rather to follow, to check a certain percentage of characteristics to know what the emotion is and the adequate behavior to in the case in question. The robot is he can acting, reacting, but it can't feeling the emotion.
Right.
Okay. Donc, ma deuxième question est à un moment donné, vous avez utilisé donc pour chaque couleur un réseau résonant donc convolutionnel, je pense. Et puis à un moment donné, tu as utilisé donc un seul réseau pour le concept couleur. Donc, est-ce que c'est juste pour quand tu as utilisé une couleur à la fois, c'est la classe, on a deux classes 0 ou 1, donc soit c'est rouge, soit c'est non rouge. Et après, donc, quand tu as utilisé le concept de couleur, est-ce qu'il y avait un concept pour combiner les trois réseaux ou alors c'est un seul réseau et c'est à la fin, c'est le nombre de classes qui a changé, donc soit la classe 1, 2 ou 3, c'est-à-dire rouge ou vert ou bleu ou il n'y a pas de couleur. Donc, est-ce que c'est un seul réseau, c'est juste une couleur d'entrée, donc les features, et à la fin, on a quelle est la couleur qu'on a à la fin? Ou alors, d'après le schéma, j'ai eu l'impression que c'est une combinaison de trois réseaux à la fois. Donc,
la question est posée, celui-là. Okay, so the second question, if you remember the first question, do you remember it?
Emotion.
Okay, the second question was about how you combine the verbal and the imagistic networks. Suila understands that well, I think she misunderstood that there's a different network for every category. That's not true, but you had verbal learning and you had image learning, and she wanted to know really what the trick for combination is.
So for the emotion stuff, I mean, if I understood the question correctly, robots don't have emotion. So how am I claiming that the robot is actually showing emotions? It's not actually showing emotions. What we want to optimize for in our model is that the robot is showing behaviors that a human perceives as having a certain emotion. And we have 16 emotions like joy, sadness, confusion, understanding. And these are from psychology literature that we pulled from, arbitrarily 16, but these are from a psychology paper. And the model can give a probability distribution over those 16 emotions. So it might be 60% joy, 10% confusion, these kinds of things. And that lends itself to being useful. I mean, one is that the robot actually produces a behavior that a human is going to view as having maybe a little bit of confusion and a lot of joy. Even though the robot isn't actually feeling that, the behavior that is conveyed to the human is the important part. Because if they think that the robot is showing that emotion or feeling that emotion, they're going to treat it as if it is, and that facilitates the interaction. So even though it's not showing emotion, it kind of needs to be there, is our hypothesis or our ongoing work here. The other question of colors, there's a different classifier for each color. There's a different classifier for each word, but they're not grouped. At least the first version of it isn't grouped. It's they're all just completely independent of each other. There's a red classifier trained on red things and not red things, and an orange one trained on orange things and not red things, green, and so on. Ongoing work that I'm doing right now that we haven't actually tested is taking the more abstract concept like color and using the classifier's coefficients as input to that classifier. So it's the same idea, only its features come from somewhere else, whereas the colors came from pictures. The features came from pictures through convolutional neural networks. The color concepts, the color words features come from the coefficients of the classifiers themselves. So it's pointing at something different.
Does that answer your question, Suila?
J'ai pas compris la dernière pour la question. Est-ce que c'est un seul réseau? C'est le nombre de classes qui y avait, c'est ça?
The essence of the question was not answered. In the final outcome, when you're integrating word stuff and image stuff, is it a single network that does it, or is it some sort of?
Well, the convolutional neural network that we use to derive the vectorized representation of the object, that's one model, that's one network. But each neuron is a separate thing. So it's all kind of one network, but they're also independent of each other. But they're all part of the same model. They're all part of the same, they're all very quickly and easily accessible. That probably doesn't answer your question either. But they're part of the same model, but they all have their own independent classifier.
Okay, we have to leave that one there. Suila, if you want to know more, you should read the paper and see if that answers your question. Okay, other questions? Suila, that's it. Other questions? Okay, I'm going to give you some easy ones. I'll start with a core notion here. You called it anthropomorphizing, right? Anthropomorphizing has one meaning, but two directions. It's basically interpreting something or someone or some entity as being as if it were the result of a mental state of a thinking or of a feeling entity. Okay, not just a thinking entity, but a feeling entity. Yeah. And of course, for that, your answer is, if you anthropomorphize the robot, you're wrong. It's not a feeling entity. It's a behaving entity. Mm-hmm. And anthropomorphizing is a two-edged sword. On the one hand, we make many mistakes with it. In symbolic AI, before the symbol grounding problem, they were over-interpreting what it is that their computers were doing. And it was a mistake, it was an illusion. We projected a mental state, a human-like mental state where it wasn't. Okay.
Yep, ELIZA is a well-known example.
Pardon me?
The ELIZA system is a well-known example.
Yeah. And all the other ones that were appearing on the horizon after ELIZA.
Right.
But anthropomorphizing has a good side too, and I think Turing recognized it. Alan Turing recognized it, which is this. The reason, the criterion for the Turing test, which is the ultimate goal, which is to reverse engineer a system that can do everything we can do. Not mm-hmm. a little toy that can play chess or do this or that, which can be done in many different ways, but something that can do everything we can do. He said, we may overinterpret the toys, because we do overinterpret the toys. They're not really cognizing and they're not feeling or thinking. They're just acting as if they were. But in a way, we can never get away from that. And the closest we can get to getting away from that is to get something that can do everything we can do. And do everything we can do in such a way that we can't tell it apart from real cognizing entities. At that point, to say, well, but is that what I really want, is beginning to become an empty concern. That's the best you can do, Turing was saying, okay? Now, you're very far away from the Turing test. You're at the level of and so the question to ask is there any ground for using the word emotion at all? in anything that you're producing. Since we all agree that the robot is not feeling the emotion, it's just being projected onto it. All it's doing when it's using the emotion words, actually the emotion signals, is using data the way that your original one, which was using either verbal data or else imagistic data to come up with an outcome.
I think you're onto something, but if my robot isn't, if we can't call it emotion, then I don't think we can call anything our systems do intelligent for the same reason.
I think you're absolutely right. You're absolutely right.
So what was his name? Actually, Brian Cantwell Smith has his book called The Promise of Artificial Intelligence, and he laments this too, that people use words like understanding and intelligent and thinking and dreaming and stuff in terms of artificial neural networks, and said we need to make that better. And I mean, it could be as simple as changing the font when you put it in your paper, but yeah, it's kind of unfair and not unfair. It's what's the word I'm looking for? It's not it's disingenuous to call it emotion when it really isn't. But, and so I do try to be careful that it's human perceptions of emotion, a model of human perceptions of emotion. So, but you're right, it's all data.
Yeah. Okay, we have to, that's only a caution. It's something we have to keep in mind. We're trying to scale up to the Turing test where this will not be an objection anymore. But
right.
Turing scale is not an objection. At toy scale, it is definitely an objection.
It definitely is. But I do make the distinction that it's not actually emotion. It's just this model's prediction of what a human might think the robot is doing.
Okay, then let me get back to the point that Friedemann brought up and Art brought up, and it struck me and probably struck others as well. When you talked about point, I think what you meant by point wasn't, I'm not sure what
it was the gesture, a pointing gesture.
It was a gesture, right? It wasn't the noun, it was the action of pointing.
Yep. And
my first question is, I mean, since you want to ground, you know that grounding is not just sensory, it's sensory motor. So in order to ground words whose meaning, oh, by the way, before I even ask that, you said connotative meaning. Is that just a weasel word, or do you mean by connotative meaning?
No, I want to distinguish between the things that we're denoting and the things that we are, the things that we are kind of representing in our heads.
Well, then you really just mean connotation, because denoting is reference, right? Where that's grounding, you know, when apple refers to apple. Right. And how I feel about apples is sort of, it's there, it's real, it's felt, etc., but it's not denotation. It's just connotation.
Connotation, yeah.
Those kind of associations. Okay, fine. So back to that. When you're talking about denotative meaning of action words, doing words, not your actions, my actions, what else can you have to ground it except the counterpart, the counterpart of what you did with the sensory grounding? You talked a lot about images. Of course, it's not images, it's dynamic, visual, auditory, etc. input. But basically there's sensory input, which is passive. And there's motor output, which is active. And it's the sensation of motor output and of generating motor output that grounds those words.
I agree, but the only other thing you could do is watch somebody else do it. So if someone says, "Look, I'm pointing," you're not feeling it, though. Mirror neurons and stuff, right? And we actually kind of played with that in the paper a little bit, where the notion of mirror neurons comes as if you map directly from the visual world to the sensory motor world in our simulated muscle activations. And we got something from that too. And we thought that was worth exploring a little bit. So what you see people do and how that manifests itself in yourself actually acting it out, that's it's different obviously when you act it out yourself, because now you have the sensory motor experience. But it has to be there. And that's why I think bodies are important. That's why I'm going down the road of using robots.
Absolutely agreed. It's part of the notion of grounding, that it's grounded not just sensorially, but also motorically. So
I that's something I know, but that's something that the rest of the natural language processing community does not know. They cite your paper, and I'm pretty sure maybe about 10% of them have read it. Because it's the classic paper you cite on symbol grounding, but most people, it's all about computer vision, and that's it. There's no notion of sensory motor information, though there are some.
I get really disappointed. It gets lots and lots of citations, but every time I actually look into it, I say, you're not getting it. In fact, you're falling into the symbol grounding problem. Let me ask you another question. Abstraction. I asked you before what you meant by concrete, and you sort of answered, but it's a hard thing. When we do the dictionary analysis, it's really hard to sort things that way. The Breisbart database gives you not just age of acquisition and frequency, but it also gives you concreteness, abstract.
Gives you concreteness, of course,
but it's not clear what they're talking about. And yeah.
Those didn't, that was another thing I looked at. I looked at the dictionary of age of acquisition for the words and the definitions, and I told you the results. I tried it for concreteness and it was messed up. It was kind of a random mess. And part of that might be because we learn lots of, I mean, we're learning concrete words throughout life and we're learning abstract words fairly early. So I don't, anyway, yes.
It's not just the Breisbart database that's in a mess. It's our idea of what we mean by concrete and abstract. You're getting close to it when you start to talk about abstraction, which is surely part of the story. Let me make a suggestion, and then we're getting close to the end of the end. Not only is the sensory input and motor output essential to grounding, but abstraction is something you do with the input. Okay, if you see a red apple, by the way, you can go lower down. I don't like any of the prototypes and the basic object stuff from Roche, but you can go lower down than an apple. You can talk about a Macintosh. You can even talk about, right, a Macintosh apple or a Golden Delicious, and you can go even lower. So there seems to be a hierarchy there. They're all concrete in the sense that there's stuff you can eat and see, but there's something else going on there, and that is in order to categorize objects at a certain level, you have to be able to abstract certain features and ignore other features. And that's what abstraction is. It doesn't lead from something that's 100% abstract to something that's 100% concrete. It leads from the sensory motor experience to increasingly abstract categories. And categorization is abstraction.
Right. So that's what I am trying to get at with this. And this is one thing I want to convey to my colleagues in the natural language processing world. So the words as classifiers model that I showed you, it uses raw input from images, represented somehow, not completely raw, but represented somehow. And then it comes up with a category. And what the classifier is doing is that it's doing feature selection. It's the coefficients determine what the important features are. You can prune the ones off that aren't so important if you'd like to. And the reason why I thought the color classifier pointed at the coefficients was so compelling and interesting is because it's a different level of abstraction that's looking at something different. It's not looking at the percepts anymore. It's looking at what the abstractions, the first level of abstractions were, and then I'm going to abstract another level on top of that. And I know you've done a lot of work in this area, and I'm going to familiarize myself with that a lot more than I have in the past. But the problem I have right now and this stuff is all in the cognitive science literature, and it's this part of the symbol grounding problem. But the thing that my colleagues do in the natural language processing community is make the assumption that that doesn't exist, or at least that we don't need to worry about it. We're going to get everything we need from text alone. So like the BERT model, the Word2Vec stuff, all the embeddings are trained only on text, and they don't care about the visual world. And the way I look at that is that they are assuming that there are no concrete words, or at least that we're not going to train them or learn them in such a way that they ever were concrete to begin with. I don't know if that makes any sense, but that means that there aren't core competencies. There is no body, there is no image, there are no eyes, there is no anything to where I can take the BERT model, hand it an apple and ask it a simple binary question. What would you say this is? Is this red or is it not red? It can't say anything about it. It can only say something like, well, red, that's over here clustered in an n-dimensional space with green and blue and purple. I think I can even reliably say it's a color and categorize it nicely, but I can't actually instantiate some percept and ask it to determine if it fits in that class of things or not. And I think when things are learned that way, they're missing a lot of semantic information that they shouldn't be missing when you just get stuff from text.
I think you're right. And I hope you gave a terrific talk. I hope you'll come back for some of the others because it's going to be a lot of.
I definitely will. This is great.
Okay. Thank you, everybody. And I'm
Thank
going to
you.
now turn off the recording because, all right, I think I can do it.